Hello everyone, this is my Physics 2211 Lab 4 on oscillations. The purpose of this lab is to investigate the motion of an oscillating mass, in this case a mass attached to a spring, and to determine how this mass's motion is related to the energy principle. Newton's second law was used as well as energy broken up into its different parts: kinetic energy, gravitational potential energy, and spring potential energy. In the end, the energy principle was proven too, as the system's total energy remained constant throughout the motion. So let's look a bit deeper at momentum and the energy principle. Newton's second law, also known as the momentum principle, relates the net force interaction to the observed motion of a system, and it's used for iteration. The energy principle states that a system's change in energy is equal to the work done by the surroundings plus the thermal energy exchanged with the surroundings. In addition, in a closed system, the change of energy is always zero. So the sum of all the different energies present in the system is also equal to zero. In this particular experiment, the different energies are kinetic energy, K, spring potential energy, US, and gravitational potential energy, UG. And their formulas are shown here. Some of the initial conditions were found using the tracker software. So the system is the mass, the spring, and Earth. There's nothing in the surroundings. The mass is about 0.4 kilograms. The stretched length of the spring is 0.7 meters, and the initial position and initial velocity, which is 0 because it's at rest, was found using the tracker software. The rest of the initial conditions had to be calculated using the tracker software data. So oscillation period, or T, was found using simply the graph generated by the tracker software here. Spring stiffness K did have to be calculated using the given formula, and it was found to be around 6.9 Newton per meter. And the relaxed length of the spring was found to be this given formula, and it's about 0.12 meters. Next, a model was generated using GlowScript code. First, the initial conditions were put in. The first image shows the mass, initial position, and initial velocity of the ball. The next image shows some constants we put in, like the gravitational constant, spring constant, and relaxed length of the spring. And then finally, the last image shows the spring force and the total energies. Finally, the code is written for the spring's motion, which is basically an iteration loop that calculates the change of energy in every loop. So first, the gravitational force and the spring force were added to find the total net force, right here. Once you find the total net force, it's easy to find the velocity of the ball and the position of the ball using Newton's second law. And once we have the velocity and the position, we can find the change in spring potential energy, gravitational potential energy, kinetic energy, all that right here. And then, using those different energies, sum them together to find the change in total energy over here. Comparing the computational model with the real-world data, we can see that they're remarkably similar. On the left-hand side, the image is of the x position versus time, and the right-hand side is y position over time. So as you can see, for both of them, the real-world and computational model started out very, very similar, almost on top of each other to begin with, but eventually they started to separate, more so in the x position than the y position. This is likely due to the fact that in the real world, this isn't a closed system. There's other forces acting on this system, like drag force and things. And also, the real world data was calculated by hand using the tracker data, so that might have also resulted in some small errors. But overall, we can see that in general, the trends are similar. What does it mean? Question number 1. Is the energy principle satisfied? Yes it is. The energy principle states that over time, the change in energy will always be 0. While the blue, red, and green lines representing the different parts of the energy are always constantly changing, the orange line, which is the total net energy, remains completely constant at 0 the entire time, satisfying the energy principle. Finally, the oscillation periods for the x and y directions. Using the graphs we generated earlier for x-axis versus time and y-axis versus time, we're able to find the period in x direction, which is about 1.6 seconds, and the period for the y direction, which is about 1.2 seconds. Notice that these two periods are not the same. Earlier, we noted that the formula for k, the spring constant, is equal to 4 pi squared m over t squared. T, being the period, is different for x and y. Therefore, the spring constant is different for x and y, despite it being the same spring. This has some interesting implications on the properties of the spring itself, and this means that the variations in period are due to the physical properties of the spring.